Welcome to today's problem walkthrough. We're tackling problem number 1510, Stone Game 4. This is a classic game theory problem that challenges us to think strategically and optimize our decisions. Whether you're preparing for interviews or exploring algorithmic game theory, this problem is an excellent opportunity to enhance your skills. Let's dive in. In this problem, Alice and Bob are playing a game where they take turns removing stones from a pile. Alice always goes first, and the twist is that on each turn, a player can only remove a non-zero square number of stones. For example, they can remove 1, 4, 9, or any other perfect square that is less than or equal to the number of stones currently in the pile. If a player cannot make a valid move, they lose the game. Now, given a pile with n stones, your goal is to determine whether Alice will win the game, provided that both players always play optimally. The input is a single integer n, which represents the number of stones in the pile, and it ranges from 1 to 100,000. The output is a Boolean value, true if Alice can guarantee a win, and false if Bob can force a win. The challenge here lies in understanding the optimal strategies that the players can use to maximize their chances of winning. To illustrate how the game works, let's look at the first example. Here, the input is n equals 1, meaning there is just one stone in the pile. Alice goes first, and since 1 is a perfect square, she removes the only stone, leaving the pile empty. At this point, Bob cannot make a move, so Alice wins the game. The output for this case is true, as Alice has a guaranteed winning strategy. This example highlights a simple scenario where the outcome is straightforward due to the small size of the pile. Now, in the second example, the input is n equals 2. Alice starts the game, and since the only square number less than or equal to 2 is 1, she removes one stone, leaving one stone in the pile. It's now Bob's turn, and he removes the remaining one stone, leaving the pile empty. Alice is then unable to make a move, so Bob wins. The output here is false, as Bob has the guaranteed winning strategy when both players play optimally. Let's examine a more complex scenario with n equals 7. Alice goes first and has two possible moves. She can either remove one stone, leaving 6 stones, or remove 4 stones, leaving 3 stones. Regardless of which move Alice chooses, Bob has a counter strategy to force Alice into a losing position. For example, if Alice removes 1 stone, leaving 6, Bob can remove 4 stones, leaving 2. Alternatively, if Alice removes 4 stones, leaving 3, Bob can remove 1 stone, again leaving 2. In either case, Bob sets up a situation where Alice cannot make a winning move, leading to her loss. The output for this example is false, as Bob can always secure a win. The problem also comes with constraints, including the pile size limit of up to 100,000 and the fact that only square numbers can be removed. This makes it crucial to account for edge cases like small inputs, large inputs, perfect square numbers, and even scenarios involving prime numbers, as they can significantly influence the strategies and outcomes of the game. To solve the Stone Game 4 problem, we can start by considering a brute force approach using exhaustive recursion. Here's the intuition: the game is simulated recursively, where on each turn, the player removes a square number of stones and gives the turn to the opponent. The base case is simple: when there are no stones left, the current player loses. For implementation, we iterate over all square numbers less than or equal to the current number of stones, remove that square, and recursively check if the opponent would lose in the new configuration. If there's at least one move that forces the opponent into a losing position, the current player wins. However, the time complexity of this approach is exponential because we repeatedly calculate results for the same values of n, leading to significant inefficiency. The recursion stack also grows linearly with n, making it memory intensive. These drawbacks motivate us to explore a more optimized solution. Instead of recalculating results repeatedly, we can leverage the problem's overlapping subproblems and optimal substructure properties to design a dynamic programming solution. The crux of the strategy is this: if the current player, say Alice, can make a move that forces Bob into a losing position, Alice wins. Conversely, if every possible move by Alice allows Bob to win, Alice loses. To formalize this, we define a DP array, DP, where DP, I, is true if the player whose turn it is can win with I stones, and false otherwise. The base case is straightforward: if there are no stones, the current player loses, so DP, 0, equals false. For the transition, we check if there exists a square number k squared such that removing k squared stones leaves the opponent in a losing position, i.e., dp I k squared equals false. Using this logic, we pre-compute square numbers and fill the dp array iteratively from 1 to n. By the end, dp n tells us whether the first player can force a win within stones. This approach is not only systematic but also significantly more efficient than brute force. The dynamic programming approach has a time complexity of O, n sqrt, n, where for each number of stones I, we iterate over all square numbers less than or equal to I. The space complexity is O, n, to store the dp array. This optimization avoids redundant calculations by reusing pre-computed results, making it an efficient solution even for larger values of n. The code implementation reflects this process. We initialize a dp array of size n plus 1, iterate through each stone count, and for each count, evaluate the possible moves by checking all square numbers. If removing a square number leaves the opponent in a losing position, we mark the current state as a winning state. This efficient approach balances clarity with performance, making it ideal for the constraints of the problem. When comparing the two approaches, brute force is easy to understand and implement but suffers from exponential time complexity, making it infeasible for large inputs. On the other hand, dynamic programming provides a polynomial time complexity solution by leveraging pre-computed results, making it optimal for this problem. The trade-off comes in the form of additional memory usage for the dp array, but this is a small cost for the significant performance boost. The key insight that allowed us to formulate the dp solution was recognizing that the problem boils down to determining a win or loss state for each n. By focusing on whether the opponent can be forced into a losing position, we simplified the problem into manageable subproblems. This realization was the turning point, making the dp approach both intuitive and effective for solving Stone Game 4. To solve Stone Game 4, we first need to clearly define the problem. In this game, two players take turns removing stones from a pile, but the twist is that the number of stones removed must be a perfect square, such as 1, 4, or 9. The player who cannot make a move loses the game. The task is to determine if the starting player has a guaranteed winning strategy for a given pile size n. The base case of the problem is simple. When n is 0, the pile is empty, and the current player cannot make any moves, meaning this is always a losing state for that player. From there, we simulate the game recursively. For each pile size n greater than 0, we consider all valid moves where the current player removes k-2 stones, where k-2 is a perfect square that is less than or equal to n. After making this move, the opponent is left with a smaller pile size, n k-2. We then check recursively whether the smaller pile size leaves the opponent in a winning or losing state. Now, we determine the state of the current player based on the possible moves. If the current player can make at least one move that forces the opponent into a losing state, then the current player is in a winning state for the pile size n. On the other hand, if every possible move leaves the opponent in a winning state, then the current player is in a losing state for n. To make this recursive approach efficient, we use memoization. By storing the results for each pile size n in a table, we avoid recalculating the same states multiple times. This optimization significantly reduces the time complexity of the solution. The key insights here are that the problem is naturally recursive, as it breaks down into smaller subproblems after each move, and that a player can only secure a win by leaving their opponent in a guaranteed losing state. Without memoization, the recursive solution would be computationally expensive, but with it, we achieve a much more efficient implementation. To implement the solution, we rely on specific data structures and steps. The primary data structure is a memoization table, represented as an array dp, where dp, I, indicates whether the starting player has a winning strategy for a pile of size I. Initially, all values in the table are set to -1, indicating that those states have not been computed yet. Additionally, we need to generate all possible perfect squares up to the pile size n, as these represent the valid moves at each step. The first step is initialization. Given the pile size n, we create the memoization table dp with a size of n plus 1 and initialize all values to -1. The base case is straightforward. When the pile is empty, no moves are possible, so we set dp 0 to 0, indicating a losing state for the current player. The next step involves filling in the memoization table through recursive transitions. For each pile size I ranging from 1 to n, we iterate over all valid moves, which correspond to perfect squares k-2 such that k-2 is less than or equal to I. For each move, we check the state of the opponent after removing k-2 stones. If there exists any move that leaves the opponent in a losing state, where dp I k squared equals 0, we set dp I to 1, indicating a winning state for the current player. If all possible moves leave the opponent in a winning state, we set dp I to 0, marking it as a losing state for the current player. Once the table is fully populated, the result for the starting player's strategy can be found in dp n. If dp n equals 1, the starting player has a winning strategy, and we return true. Otherwise, we return false. Let's walk through an example to illustrate how the algorithm works. Suppose the input is n equals 7. We start by initializing the memoization table as dp equals 0, -1, -1, -1, -1, -1, -1, -1. The base case is set with dp 0 equals 0, indicating a losing state for the current player when the pile is empty. Now, we compute the state for each pile size. For I equals 1, the only possible move is to remove 1-2 equals 1. This leaves the opponent with a pile size of 0, which is a losing state, so we set dp 1 equals 1. For I equals 2, the only possible move is again 1-2 equals 1. This leaves the opponent with a pile size of 1, which is a winning state, so we set dp 2 equals 0. Similarly, for I equals 3, removing 1-2 equals 1 leaves the opponent in a losing state, so dp 3 equals 1. For I equals 4, the possible moves are 1-2 equals 1 and 2-2 equals 4. Removing 4 leaves the opponent with a pile size of 0, so we set dp 4 equals 1. We continue this process until dp 7 is computed. The final result is dp 7 equals 0, meaning the starting player cannot guarantee a win, so we return false. Finally, let's analyze the complexity of the solution. The time complexity is O, n asterisk sqrt, n. For each pile size I, we iterate through all perfect squares k-2 such that k-2 is less than or equal to I. The number of perfect squares up to I is approximately sqrt, I, and summing this over all I from 1 to n gives the overall complexity. The space complexity is O, n, because we use a memoization table dp to store the results for all pile sizes from 0 to n. This efficient use of time and space ensures that the algorithm can handle reasonably large inputs without excessive resource usage. This implementation solves the LeetCode problem number 1510, Stone Game 4 using dynamic programming. The goal is to determine whether the starting player has a winning strategy for a given number of stones n. The solution uses a dp array where dp I represents whether the starting player can win with exactly I stones. The base case is straightforward, dp 0 is false because if there are no stones left, the player who is supposed to play loses. The algorithm iterates through all pile sizes from 1 to n. For each pile size I, we check all possible perfect square numbers, e.g. 1, 4, 9, that can be removed. If removing a perfect square j*j leaves the opponent in a losing position, dp I j*j equals false, then dp I is set to true because the starting player can force their opponent into a losing state. The inner loop stops as soon as we find a winning move for the current pile size I. This ensures that the solution is efficient and avoids unnecessary calculations. Finally, the function returns dp n, which indicates whether the starting player has a winning strategy for the given pile size n. The time complexity of this solution is O, n asterisk sqrt, n, because for each I from 1 to n, the inner loop runs up to the square root of I. The space complexity is O, n, for the dp array. This is the Java implementation of LeetCode problem number 1510, Stone Game 4. The solution mirrors the Python logic, utilizing dynamic programming to determine if the starting player can win given n stones. The dp array is used to store results for smaller subproblems, and the logic checks for all possible perfect square moves. Key differences include Java's explicit type declarations and array indexing. To solve the problem, we use dynamic programming to determine if the starting player can win given a certain number of stones. For the first example, with an input of n equals 1, we begin by initializing a dp array of size n plus 1, where each value is initially set to false. This array will help us track whether the starting player can secure a win for each number of stones from 0 to n. In this case, dp starts as false, false. Then, we iterate through values of I from 1 to n. For I equals 1, we calculate all possible moves by removing a perfect square number of stones. Starting with j equals 1, we check if j asterisk j is less than or equal to I. Since 1 asterisk 1 equals 1 is valid, we evaluate dp I j asterisk j, which is dp 1 to 1 equals dp 0. Since dp 0 is false, it means the opponent loses if we leave them with 0 stones. Hence, we set dp 1 to true, indicating that the starting player can win when there is 1 stone. Finally, the dp array becomes false, true, and we return dp n, which is true. This means the starting player wins by removing the only stone, leaving the opponent with no moves. Now, let's analyze a scenario with n equals 7. Again, we initialize the dp array with all values set to false, resulting in dp equals false, 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 false. We iterate through values of I from 1 to 7. For I equals 1, removing 1 stone leaves the opponent with 0 stones, a losing position, so we update dp 1 equals true. For I equals 2, removing 1 stone leaves the opponent with 1 stone, which is a winning position for them, so dp 2 remains false. Similarly, for I equals 3, removing 1 stone leaves the opponent with 2 stones, also a position where they can win, so dp 3 equals false. At I equals 4, removing 1 stone leaves the opponent with 3 stones, which is a losing position, so dp 4 equals true. Additionally, removing 4 stones is another valid move, but it also leaves the opponent in a losing position. Thus, dp 4 remains true. This process is repeated for values of I up to 7. For I equals 5, removing 1 stone leaves the opponent with 4 stones, which is a winning position for them, but removing 4 stones leaves the opponent with 1 stone, a losing position. Hence, dp 5 equals true. For I equals 6, removing 1 stone leaves the opponent with 5 stones, which is a winning position, meaning dp 6 equals false. At I equals 7, removing 4 stones leaves the opponent with 3 stones, which is a losing position, so dp 7 equals true. After completing the iterations, the final dp array becomes false, true, false, false, true, true, false, true. Based on this, we return dp 7 equals true. The starting player can win by removing 4 stones, leaving the opponent with 3 stones, which is a losing position. This demonstrates how the dynamic programming approach ensures we explore all possible moves and their outcomes to determine the result. In the final example, with n equals 17, we follow the same dynamic programming process. We initialize dp as false, *18 and iterate through values of I from 1 to 17. At I equals 1, removing 1 stone leaves the opponent with 0 stones, so dp 1 equals true. For I equals 2 and I equals 3, removing 1 stone leaves the opponent in a winning position, so both dp 2 and dp 3 are false. At I equals 4, removing 1 or 4 stones leaves the opponent in a losing position, so dp 4 equals true. This logic is repeated for all values up to I equals 17. After computing the outcomes for each I, the final dp array becomes false, true, false, false, true, true, false, true, true, false, true, true, false, true, false, false, true, true. We return dp 17 equals true, indicating that the starting player can win by following an optimal strategy. This involves removing a perfect square number of stones at each step, always leaving the opponent in a losing position. This example highlights the power of dynamic programming to efficiently solve the problem for larger inputs. The time complexity of the winner square gain function is O, n asterisk sqrt, n, asterisk asterisk, and we can break this down step by step. First, the outer loop iterates over all pile sizes from 1 to n, which contributes O, n, iterations. Within this outer loop, there is an inner loop that checks all perfect squares less than or equal to the current pile size I. This inner loop runs approximately O, sqrt, I, times because it iterates over integers j and checks the condition j(2 equals I. Combining these two loops, the total work involves summing the square root of each pile size, or sum sqrt, I, for I from 1 to n. Using mathematical approximations, this summation evaluates to O, n asterisk sqrt, n, asterisk asterisk in the worst case. Therefore, the overall time complexity is dominated by this term, making it O, n asterisk sqrt, n, asterisk asterisk. The space complexity of the winner square game function is O, n, and here's why. The primary component contributing to space usage is the dynamic programming array dp, which has a size of n plus 1. Since this array stores Boolean values for each pile size, it requires O, n, space. Additionally, the function uses a few auxiliary variables such as I for the outer loop and j for the inner loop. These variables require only constant space, or O, 1. As a result, the space complexity is determined by the dp array, making the overall space complexity O, n. To compare the dynamic programming approach with a brute force solution, consider the naive recursive method. Without dynamic programming, the function would recursively evaluate all possible moves for each pile size, leading to an exponential number of recursive calls. This results in a time complexity of O, 2 to the power of n in the worst case, as each state branches into multiple recursive calls. The space complexity for this approach would be O, n, due to the recursion stack depth. In contrast, dynamic programming optimizes this process by storing intermediate results in the dp array, eliminating redundant calculations. This optimization reduces the time complexity from O, 2 to the power of n, to O, n asterisk sqrt, n, asterisk asterisk, which is a significant improvement. The space complexity remains O, n, making the dynamic programming approach not only more time efficient but also just as space efficient as the naive method. When analyzing the best, average, and worst cases, the time complexity of O, n asterisk sqrt, n, asterisk asterisk remains consistent. Even in the best case, where n is a perfect square and the first move could potentially lead to a win, the function still evaluates all states up to n, so the time complexity does not change. For the average and worst cases, the function must consider all states and evaluate all possible moves for each state, resulting in the same overall time complexity of O, n asterisk sqrt, n, asterisk asterisk. To mathematically verify this, note that the inner loop runs up to sqrt, I, for each pile size I, and the outer loop iterates over all values from 1 to n. Summing these iterations gives some sqrt, I, for I from 1 to n. Approximating this sum using integration yields 2/3 asterisk n caret 3/2, which simplifies to O, n asterisk sqrt, n, asterisk asterisk. This confirms that the time complexity holds across all cases. When solving the Stone Game 4, there are a few common mistakes to watch out for. First, it's important to consider all valid moves, which means using all possible square numbers less than or equal to the current number of stones. For example, while numbers like 1, 4, and 9 are common, overlooking higher square numbers can lead to an incomplete solution. Next, always ensure the base case in your recursion is correctly defined. If the base case, such as when there are 0 stones left, isn't handled properly, you risk infinite recursion or incorrect results. Another frequent error is recalculating the same states multiple times in a recursive approach. Without memoization, this can severely impact the time complexity, as the algorithm ends up performing redundant computations. Finally, don't overlook edge cases. For example, scenarios like starting with just one stone, where only one move is possible, or situations where a specific move determines the winner, can expose gaps in your solution if not handled thoroughly. Now, another critical point to keep in mind is that greedy strategies, such as always removing the largest square number, might seem intuitive but often fail in edge cases. Optimal play sometimes requires taking smaller moves initially to set up a win later. Shifting to interview-specific insights, many game theory problems, including this one, revolve around identifying the winning state through recursion and memoization. A key insight here is that the solution is all about determining whether the current player can force the opponent into a losing position. This is why understanding optimal substructure matters. The game's state depends solely on the remaining stones, which justifies using dynamic programming. Lastly, make sure you're ready to discuss the complexity trade-offs. While naive recursion has exponential complexity due to repeated calculations, memoization significantly improves this to O, n asterisk sqrt, n, making it more efficient and scalable. It's also worth exploring related problems to deepen your understanding of these concepts. LeetCode 877, for instance, is another two-player game theory challenge, where the goal is to devise optimal strategies. LeetCode 1140 builds on this concept, adding more constraints and strategic depth. LeetCode 464, Can I Win, shifts the focus to determining if the first player can guarantee a win given a specific set of moves. Though not strictly a game theory problem, LeetCode 319, Bulb Switcher, is also valuable for practice, as it involves reasoning with square numbers, which is a core part of Stone Game 4. Exploring these problems can provide additional perspectives and strengthen your problem-solving skills in this domain. Finally, let's discuss some alternative approaches to solving this problem. A bottom-up dynamic programming method can be a good alternative to recursion. Here, you use an iterative DP array where each entry represents whether the player can force a win with a specific number of stones. This approach avoids the overhead of recursion and can be easier to debug, though it might be slightly more complex to implement. Another option involves leveraging mathematical observations. By analyzing the properties of square numbers or applying insights from related concepts like NIM games, you might simplify the problem or even discover faster solutions. However, while greedy heuristics might seem appealing for quick approximations, they should generally be avoided for this problem, as they often fail to handle critical edge cases. Stick to methods that ensure correctness and scalability, especially when preparing for interviews. Great job! We've covered Stone Game 4 and discussed the brute force approach. Remember, recursion is often just the first step. Optimization is key. Keep practicing, and don't hesitate to revisit this problem as you refine your skills. Thanks for watching, and I'll see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!